Hi, my name is Moritz Böhle and I'm a PhD student at the Max Planck Institute for Informatics in Saarbrücken. I'm very happy to present to you today our work on convolutional dynamic alignment networks for interpretable classifications. The problem that we aim to address with our work is the fact that deep neural networks are essentially black boxes. Of course, many methods trying to overcome the black box nature have been developed. For example, here I show importance attributions for individual classification decisions according to some commonly used explanation methods. In particular, red colors in these heat maps denote positive importance values and blue colors denote negative importance values. However, given the opaqueness of the network models to start with, it is in general unclear whether and how well these methods actually reflect the underlying model. Therefore, we approach this problem from the other side. In contrast to deriving post-hoc explanations for existing models, we design a novel network architecture for which we carefully constrain the modeling process in the first place. By doing this, we obtain models which we understand better, which in turn allows us to derive model-faithful explanations for them, as for example shown here on the left. So in contrast to conventional classification models, which produce a class label but lack an explanation for their prediction and thus require post-hoc explanations, we are proposing a model that inherently produces a model-faithful linear decomposition of the predicted class logic. In the following, I will give a high-level overview over how the convolutional dynamic alignment networks, or CoDA Nets for short, work. As shown in the sketch, a CoDA net consists of multiple CoDA layers, which in turn are defined by two main properties. These properties are dynamic linearity on the one hand and boundedness on the other hand. But what does that mean and why is this important? Let's start with dynamic linearity. So, dynamic linearity describes the fact that each layer explicitly computes a linear transformation of its input by applying an input-dependent matrix WL+1. The benefit of this is, of course, that this allows to decompose the entries in the output vector of the layer in terms of contributions coming from individual input dimensions j. Moreover, by explicitly normalizing the rows of the dynamically computed matrix, we can bound the magnitude of those entries in the output vector. This has an important ramification. In particular, it means that large outputs can only be achieved if the dynamic weights are well aligned with the input. In other words, in order to propagate large signals from layer to layer, the network has to model the input distribution at each layer such that the dynamically predicted weights are a good angular reconstruction of the input. Importantly, these two constraints, namely dynamic linearity and boundedness, are specifically chosen such that they are inherited by the network as a whole. A CoDA net is both dynamic linear and has an output bound that is independent of the network parameters. Similar to the outputs of a CoDA layer, the outputs of a CoDA net can therefore be decomposed into individual input contributions coming from specific input dimensions, for example pixels. The boundedness, on the other hand, ensures that the global linear transformation matrix, which is denoted here by W0 to L, aligns with discriminant features in the input. But now let's have a look at the results. First, as expected, we find that the CoDA nets indeed learn to align the dynamically computed weights with discriminant features in the input during network optimization. The resulting contribution maps are good explanations of model behavior, which we evaluate both qualitatively, as we show here for example, as well as quantitatively, according to two common metrics for measuring the quality of heat map-based explanations. Under both metrics, we find that the model inherent explanations consistently outperform post-hoc explanations. Moreover, we show that CoDA nets are performant classifiers, and they achieve accuracies that are on par with models from the ResNet model family, both on CIFAR10 as well as TinyImageNet. We will soon release an updated version of the CoDA nets that improves their scalability. But most importantly, with the CoDA nets we show that it is possible to design neural network architectures with built-in interpretability. This is achieved by restricting how the neural networks are supposed to solve a specific task, in our case via alignment, which then allows us to decompose the network outputs faithfully in terms of input contributions. Thank you very much for your attention and make sure to check out our website for code and updates on the CoDA networks.